Hello friends, I am Professor D.G. Trivedi going to take your third lecture regarding separation of variables. Using this method, we are going to deal with the third example using Cartesian coordinate system. That we are using a Cartesian coordinate system and will solve the Laplace equation using method of separation of variables. This example is like this. An infinitely long rectangular metal pipe, sides A and B, is grounded, but one end at x is equal to 0 is maintained at a specified potential V0, which is a function of yz because it is a plane yz, as indicated in figure 3.22. Find the potential inside the pipe. You can see this thing in this figure. This figure indicates that there is a rectangular pipes, right? This rectangular pipes are infinity at x is equal to infinity, and all these sides of the pipes are grounded. That means all these metal pipes are grounded and they are kept at a potential 0. At x is equal to 0, this pipe is going to be close with some another metal plates where the potential is V0, which is a function of y and z over this metal plate. So this way, this is the boundary conditions is given to you, and this is a problem we have to solve for the Laplace equation. That means we have to find out a potential V inside this pipe. How to find out? Again, the same way we have done in the previous two examples. But the previous two examples were two-dimensional Laplace equation. Here, in this particular example, it is three-dimensional Laplace equation we have to solve. That means we have to solve the potential for x, y, z. And hence, the Laplace equation is del square V upon del x square plus del square V upon del y square plus del square V upon del z square. This is equal to 0. This is a partial differential equation. This we have to find out for the potential. Subject to the boundary conditions. Now boundary conditions are given. All four sides are at ground potential. That means you can see that first boundary condition, potential V is equal to 0, where y is equal to 0. Potential V is equal to 0, another plate which is kept at y is equal to a. That is also kept at a ground potential. V is equal to 0 when z is equal to 0, and V is equal to 0 when z is equal to b. That means all the four plates which are preparing this pipe, they are kept at a potential 0. Now at x is equal to 0, the potential is maintained is equal to V0, which is a function of y and z. That means it may be depending upon the coordinates y and z over that plate, and at x is equal to 0. And the last boundary conditions that we can assume that as we are going away from the hot strip at x is equal to 0, then the potential drops to the 0 as x tends to infinity. This way, all the six sides or boundary potential is specified, and hence we can solve the Laplace equation in the region of our interest. As always, we look for the solutions that are the product of the functions. Each function must be depend upon single variable only. That means we can look that there is a solution of this Laplace equation is a potential V. V must be function of x, y, z. That can be assumed as x is a function of small x, capital Y is a function of small y, and capital Z is a function of small z. Putting this into our Laplace equation, that is the previous equation, and dividing by V, V is equal to x, y, z, and we can find out that each term is depending upon one coordinates only. That means we can obtain like this way, and the partial differential equation is converted into ordinary differential equation. And that way 1 upon capital X d square capital X upon dx square plus 1 upon capital Y d square capital Y upon dy square plus 1 upon capital Z d square capital Z upon dz square is equal to 0. So this way we have converted a partial differential equation this into ordinary differential equation like this, second order ordinary differential equation, and each term is depending upon one variable only. That's why it is becomes ordinary differential equation. Now we can think about that each term depends upon a different variable and variables are independent of others. That means each term must be constant. So we can think about 1 upon capital X d square capital X upon dx square, that is equal to constant C1. 1 upon capital Y d square capital Y upon dy square, that is going to be another constant C2. And 1 upon capital Z d square capital Z upon dz square, that is equal to third constant C3. And hence substituting this constant in our previous equation, this we can say that this is going to be C1, this is going to be C2, and this is going to be C3. So C1 plus C2 plus C3, that is equal to 0. That way we can obtain this equation. One of the constant we can think a positive. So according to our previous exercise that we already done in the previous example 3.3, where we need that C1 must be positive and C2 and C3 is required to be negative. Because if the C1 is positive, corresponding to that, the solutions x is a function of x, capital X is a function of small x, must be a exponential solution. And if the coefficients are going to be negative, then it is a sinusoidal solution. That means y is a function of y and z is a function of z must be sinusoidal. And that's why C1 is required to be positive and C2 and C3 should be negative. Now let us set C2 is equal to minus k square and C3 is equal to minus L square. We know from here that C2 plus C3 that is equal to minus C1. So substituting this, C2 plus C3 is equal to minus k square minus L square, again minus sign, that means C1 is equal to k square plus L square. And hence we can substitute this one into our this example, this equation, that means capital d square capital X upon dx square, that is equal to coefficient C1, that is k square plus L square into capital X, and here capital D square y upon dy square is equal to C2, that is minus k square into capital Y, which is going to be multiplied from here, and similarly d square capital Z upon dz square, that is equal to minus L square, Z will be there. So this way we have separated three different equations and each depends upon one variable only, and that way using a method of separation of variable we have converted a partial differential equation into second order ordinary differential equation of three different equations. And once again the separation of variables has turned a partial differential equation into ordinary differential equation, and the general solutions for each function can be written like this way. Capital X is a function of small x, that is equal to a capital A e raised to under root k square plus L square into x. Remember this x is outside this under root, plus b e raised to minus under root k square plus L square into x. Y is a function of y, c sin ky plus d cos ky. This is sinusoidal function because C2 was negative. And z is a function of z, capital E sin Lz plus capital F cos Lz will be there. Here this A, B, C, D, E and F are constant of integration. They can be obtained by taking the 2 times integrations of our previous ordinary differential equation, and we will get this general solution. That means if there is a 3-dimensional problem is there, up to this we get the general solutions. We have still not imposed any boundary conditions. That means this is the most general equation or most general solutions to the three-dimensional Laplace equation. And for any problem, you can write down directly these equations. Now, to get the specific solutions to our problems, we are going to impose one by one boundary conditions to our this general solutions. So, applying a different boundary condition like this, that if we supply a boundary condition 5, what is that boundary condition? X tends to infinity, then the potential was tends to 0. That implies that A has to be 0. So this boundary condition 5 implies that constant of integration A has to be 0, otherwise this boundary condition will not be satisfied. Similarly, boundary condition 1 says that at y is equal to 0, the potential was 0. This implies that D must be 0. And condition 3, which says that z is equal to 0, the potential must be 0 because that is given. So this yields that f must be 0. So this way, these three coefficients a, capital D and f in our previous example has to be 0. A, D and f has to be 0. Remains this and this. That means they are going to be in a multiplication. B, C and E. Now at y is equal to A also, this equation is going to be 0. At z is equal to B also, this equation is going to be 0. That means how that can be obtained? That means that sine ky, ka, that is equal to n pi, and sine L is nothing but mz n pi n mz, that is equal to n0, implies that L must be equal to m pi, and which gives us this requires that means the condition 2 and 4, that means y is equal to A and z is equal to B, requires that k is equal to n pi upon A and L is equal to m pi upon B, what we have obtained in a previous case. Whereas n and m must be some positive integers starting from 1, 2, 3, etc. Combining this remaining constant, we left with the equation that means v is a function of x, y, z, that is equal to absorbing the remaining coefficients capital B, capital C and capital E. We can write one coefficient, that is going to be capital C. So this coefficient is going to be the C, e raised to minus pi under root, because n pi was there and n pi whole square, that means pi square was here, pi square was here, and taking the under root, that pi comes out. So minus pi under root n upon a whole square plus m upon b whole square into x into sine n pi y upon a sine m pi z upon b will be there. Now we have seen that this equation is having a property of completeness. That means we are not getting a single solutions, but we are getting a set of the solutions. This solutions meets all the boundary conditions except the condition 6. It contains two unspecified integers n and m, and the most general linear combination can be obtained as a double sum, because we have seen in a previous case also. That means we are not getting a single solutions, but we are getting a set of the solutions where n is equal to 1, 2, 3, etc. and m is equal to 1, 2, 3, etc. That means there are so many constants is there, so many solutions v12, v13, v14 like that way, and v21, v22, v23 like that way. So many solutions are going to be obtained, and that means combining this all the solutions, we can take a linear sum of these solutions, and that is nothing but the double sum will be there. That means our most general solutions So after adding all the boundary conditions, we are getting v is a function of x, y, z that is equal to double sum. N is equal to 1 to infinity, m is equal to 1 to infinity, c n m e raised to minus pi under root n upon a whole square plus m upon b whole square into x sine n pi y upon a into sine m pi z upon b. This is our solutions. But still the sixth boundary condition is not satisfied here. But there is some coefficient C and M which is buried in this equation. If we find out that coefficient, then this condition, six conditions can be satisfied. So to substitute the sixth boundary condition, we have to put x is equal to 0. That means if we substitute x is equal to 0, potential is specified. V0, which is a function of yz. So we'll substitute the sixth boundary condition and we'll find out the value of the coefficient C and M, which is buried in this equation. So all the boundary conditions can be satisfied and we can find out our specific solutions to our problem. So now let us hope to fit the remaining boundary conditions. V is a function of x is equal to 0, so I put it 0 here, and yz. This is equal to double sum. N is equal to 1 to infinity, m is equal to 1 to infinity, c n m is there, into sine n pi y upon a, sine m pi z upon b. This is equal to, we substituted that potential is specified on this boundary, that is v0, which is a function of yz. This is, let us say, equation 3.49. By appropriate choice of the coefficient C and M, which is buried in this one, we can satisfy the equation 6. And that way, we can obtain specific solutions to our problem. And to determine this coefficient, what we have to do? Whatever we have done in the previous example. That means, here you can see that this is a Fourier sine series, and using the Fourier sine trick, Fourier trick, we can find out the value of the coefficient nm, which is buried into Fourier sine series, and that way we can find out our required coefficients. To determine this constant using a Fourier trick, we must multiply both the sides of this equation, left side and right side, by sine n dash pi y upon a, sine m dash pi z upon b, where n dash and m dash are arbitrary positive integers, and we can integrate from the limit from 0 to a as well as from 0 to b, and that way we can find out the coefficient C and M. Substitute in this equation, v is a function of 0, y, z, that is equal to double sum. N is equal to 1 to infinity, m is equal to 1 to infinity, C and M, 0 to a, sine n dash pi y upon a, sine n pi y upon a dy. That means this is the integration over y. Similarly, there is another coefficient, that is m integer is there. So we are taking the integration from 0 to b, sine m dash pi z upon b into sine m pi z upon b dz. This is the integration over the variable z. This is equal to, on the right hand side, double integration 0 to a, 0 to b, v0, which is a function of yz, sine n dash pi y upon a, sine m dash pi z upon b. These two terms we have multiplied left hand side, so we are multiplying on the right hand side and taking this integration dy dz from 0 to a as well as 0 to b. Now, using the property of orthogonality, left hand side of the equation becomes, what is this value of the integrations? If n dash is equal to n, then this integration is survived. For only one term of the coefficient, this integration is going to be survived, where n is equal to n dash. Otherwise, for n is not equal to n dash, the terms are going to be drop out, because that integration is going to be 0. Similarly, another integration, if m dash is equal to m, then and then only that integration is going to be non-zero, and that value is going to be v by 2. And otherwise, this integration is going to be 0. So only one term is going to be survive, where m is equal to m dash and n is equal to n dash. This integration is going to be a by 2. So we can substitute this one, and we'll see that on the left hand side only one coefficient is going to be survive, where n is equal to n dash and m is equal to m dash. So our coefficient becomes c n n dash m dash, or you can write c n m into the value of the coefficients. Value of this integration is going to be a by 2 into b by 2, and hence we can write our left hand side is equal to cnm a by ab by 4. Therefore, substituting this, we can find out the value of the coefficient cnm, that is equal to 4 by ab double integration from 0 to a 0 to b v0, which is a function of yz, sine n dash pi y upon a sine m dash pi z upon b into dy, that is right hand side, dy dz. So the equation 3.48 with the coefficient given by equation 3.50 is the solutions to our problem. So you can say that 3.48, which one? This is your 3.48, that is v is the function of x y z is equal to sigma n is equal to 1 to infinity, sigma m is equal to 1 to infinity. The coefficient cnm is equal to e raised to minus pi under root n upon a whole square plus m upon b whole square into x sine n pi y upon a sine n pi z upon b. This is our solution. With this value of the coefficient is given by the equation 3.50, which we have find out here. So this equation 3.48 is our solution with the coefficient given by 3.50. Now take a specific case for which v0y, which is a function of y and z, is a constant potential. That may be a metal plate, and if it is a metal plate, the potential is constant over all points, and it is becomes independent of y and z. So we can write v0, which is a function of yz, is equal to constant potential v0. And if it is a constant potential, then from this equation v0 yz, that is a constant term, we can take it outside of this integration, and then cnm is equal to 4v0 upon ab double integration from 0 to a 0 to b, that is equal to into integration sine n dash pi y upon a sine m dash pi z upon b dy dz. And this integration, if this integer n dash is going to be even, then this integration is going to be 0, or m is going to be even, m dash is going to be even, then also this integration is going to be 0, then the coefficient is going to be 0. That means we should see that m or n dash should not be even term. That means it should not be 2, 4, etc. These coefficient or this integers n and m, or n dash and m dash, must be odd numbers. That means 1, 3, 5, 7, etc., etc. And then this integration will be having a value of n by 2. This will be having a value of m by 2, and that way if we substitute, we'll find out the value of the coefficient cnm is equal to 16v0 upon pi square nm. If n and m both are odd, remember any one of them is even, the integrand is going to be 0 and coefficient becomes 0. So substituting this value of the coefficient in our equations, we can write now our specific solution with potential at x is equal to 0 is considering constant v0. We can write v is a function of xyz, that is equal to 16v0 upon pi square double sum. N is varying from 1, 3, 5, etc. That means odd to the infinity. M is also changing from 1, 3, 5 to infinity. That is also odd. And 1 upon nm, cnm e raised to minus 5 under root n upon a whole square plus m upon b whole square into x sine n pi y upon a sine m pi z upon b. This is the equation 3.50, which is our specific solutions to our given problem. Notice that the successive terms decreases rapidly. As we are increasing the value of n or m, the successive terms are decreasing very rapidly. And that means we can obtain our solutions by keeping first few terms only. Thanking you, friends.